So in the last class, we were discussing various energy scales we have in a solid. The electronic energy scale, the lattice vibration energy scale, and typical interaction energy scale of electron magnetic moments with external fields, as also the strength of dipole-dipole interactions inside a solid at typical atomic distances. Then we got to a discussion of why the electron spins would like to align parallelly or anti-parallelly, whatever. So what is that interaction that makes that happen? A manifestation of that at the atomic scale or at the level of a single atom is, of course, the Hund's first rule, which tells you that the spin has to be maximized, or the maximum spin configuration gives you the lowest energy state. And also, when you have such atomic moments in a solid, typically below a certain temperature, I mean, in the magnetic systems, they tend to order in the sense that they tend to, orient in definite directions relative to each other, which gives rise to long-range magnetic order. And again, the question is, what is the interaction that leads to this sort of a magnetic order? So that is the question we are now going to look at. And let me warn you here, because it involves quite a bit of algebra, and the board space I have here is severely limited. So therefore, I would try to do my best, but then I don't know, I'll realize as I go along. But you have to sort of independently try to work it out and ensure that you have got all the terms and factors correctly. So why do we start? So the first case we will look at is, we'll take a simple case of two electrons. Okay. We'll then sort of jump to the solid state situation. But right now we are talking of two electrons which can occupy two orbitals. And in the first exercise, we'll assume that these orbitals are orthogonal to each other. Okay. Before I get onto the algebra, let us see what we know about many electron systems. Suppose, so obviously, I mean, you cannot have magnetism when you have a single electron. Okay. We are talking of a many electron system, and as I was trying to emphasize last time, it will become more obvious in today's lecture, is that what is responsible for this magnetic order is the electron-electron interaction. So we have to know how to write many electron wave functions. Something you have studied in your quantum mechanics course, identical particles. So what is the sort of form of many electron wave function? How do I write a many electron wave function? Oran?
Yes, so 1 by root over n factorial.
1 by root over in factorial, yes. Then
Summation over minus I whole to the power.
Summation over minus what?
Minus I whole to the power p. Then state of the particle. Again, function of the particle.
Again, function. Then what?
Pi 1, pi 2.
There has to be a p, the summation over permutations of psi 1, psi2. So what are these i's, by the way? That's the main question.
They are antisymmetric.
No, the psi's are not antisymmetric. I mean, this whole thing is antisymmetric.
Yes.
But I'm asking, what are these individual psi i's? So what is the answer? What are these individual psi i's here?
Sir, the psi i's have two parts, one spatial part and one spin part.
See, this is the crucial part. Yeah.
They
Go
are
ahead.
single particle wave functions.
Yeah, they are single particle wave functions, but the important point to remember is that there's a spatial part and there is a spin part. Without that, you cannot write down this function for electrons, which are spin half particles. So each of these orbitals, let us call these orbitals. So each of these orbitals is a product wave function of this form, where this is a spatial wave function. So this is a function of R. And then there is a spin part. And that spin part, because electron is a spin half particle, it can be, either of up or down relative to some quantization direction. So we will denote those as alpha. So alpha for up and beta for down. So it can be either alpha or beta. And in a abstract sense, we will notation will write this. Or we'll introduce formally a variable which really is not a continuous variable, but nevertheless, we'll just write alpha or beta as functions of some variable, spin variable s, so that to formally mean and so on. And if this is alpha star alpha, then this is 1. So basically, these spin parts are orthonormal. And similarly, let us assume that the spatial parts are also orthonormal. So it's very important to remember this, that each of these is a product of a spatial wave function and a spin wave function. Now, with that, we are dealing with a 2-electron problem. So let us suppose we have, let me draw it here. We have 2 orbitals with spatial wave functions given by psi1r and psi2r with, okay, and which are orthogonal. So basically, we are trying to see what is the lowest energy configuration of 2 electrons in 2 orbitals which are orthogonal to each other. So a situation would be where you have 2 atomic orbitals that are occupied by 2 electrons, and you are basically asking the question, how should they occupy these orbitals so that the energy is minimized? Okay, now we have 2 spin half objects here, 2 spin half particles, and we know that the total spin can be either 0 or 1. So we either have a singlet state with S equal to 0, and there is a triplet S equal to 1, free state S equal to, so basically we'll have two SZ possibilities. One is a singlet and the other is a triplet with so these are simple to write down, these wave functions. So basically what I'll do now is to write down wave functions of these states in terms of phi 1, phi 2 and alpha beta. So let us try to look at these two states. These are simpler. 1 minus 1 and 1 plus 1 are simpler. So in both these states, I have Sz equal to 0. So if Sz is equal to 0, one of the electrons is in up state, the other is in down state. So I can have this, or I can have this. So this is what I have written here. If you look at this, so there are two situations, one in which the electron in the orbital phi 1 has up spin, and the one in phi 2 has down spin, and I call the product chi here. The other possibility, and because electrons are indistinguishable, I can as well have these. And I cannot distinguish between these two situations. So therefore, the sort of full two electron wave function, which is the function of R1, R2, S1, S2, is, apart from a normalization constant, is a sum that would be plus or minus. So basically, this part will give you this determinant, this later determinant. Okay, this chi1 occupied by electron 1 and chi2 occupied by electron 2, or chi2 occupied by electron 1 and chi1 occupied by electron 2. So these two are, again, because of indistinguishability, both these will appear. So you have this determinant, and then you have the other determinant where now chi1 is this. So chi1 is now chi1, electron 1 in chi1, electron 2 in chi2, or electron 1 in chi2 and electron 2 in chi1. But now chi1 and chi2 are different compared to this situation. So there are all these possibilities that you have to consider. So the first thing I want to emphasize here is that even for a non-interacting electron system, so far we haven't talked about any interaction. We are just writing down the two electron wave function, which obey the antisymmetry property, and which sort of respects the indistinguishability of the two electrons. So even there, if you, as you see, you cannot write that wave function as a single determinant. So this idea that, you know, many fermion wave function is a Slater determinant, a Slater determinant, is a very wrong idea. It can be one single determinant. It can be sum over many determinants. If you want it to be a sort of eigenstate of S squared and Sz. So both these, whether you take plus or minus, these are both eigenfunctions of S squared and Sz. Okay. So single determinant may not describe a correct SSZ state. You require more than one determinant, and these are examples of this. Now, so here I have plus or minus. So what I have written here is with the plus sign. And if you take the plus sign and you manipulate these terms, you end up getting this. So the spatial part and the spin part here separate out. Now this separation happens only when you have, in a general case, only when you have a 2-electron situation. If you have more than 2 electrons and you are writing wave function for some state is Z, unless SZ happens to be the maximal spin state, this sort of separation does not happen when you have more than 2 electrons. So something you should remember. Anyway, here this simplification happens and you have this wave function. So this, if you work out what is, so this is the spin part and this is the spatial part. And if you work out what is the A squared for this, or what is the value of S in this state, this happens to be S equal to 1. So you can work it out. So this is the triplet state, one of the triplets. This is the 1, 0 state. 0 because the 2 SZ parts are up and down, up and down. So this is SZ equal to 0 state, and S will, if you evaluate the expectation value of the S squared operator, you will find that the value of S is 1. So this is this triplet state. Had you taken the minus sign over here, you would have got, so if I take the minus sign here, this would have come with a plus sign, and this would have come with a minus sign. So in that case, so right now this is equal to 1, is Z equal to 0. If I had taken the other sign, I would have got the state with S equal to 0, and then of course Z would also be 0. So those are the two states, triplet and singlet. These, as I said, are simpler. So let me write these more explicitly. So this is one of the, yes.
So can you please once write the determinant in a bigger form? I mean, it's difficult.
Bigger font?
I mean,
bigger font.
No, I mean the latest. I mean, in a bigger size. I mean, it is difficult.
Yeah, that is what I'm telling you. I'm trying to do that, but I have only one sort of board, and this is just not sufficient. If I write even bigger, I will be running out of space sooner. Let me see what's the best I can do. Yeah, it's kind of unfortunate, but okay. So this is one of the triplets. So let me write it a little bigger here. If I had taken the minus sign, I would have got, I'm not writing the normalization, by the way. There'll be a 1/2 here. This should be 1. So this is the singlet state with S equal to 0, S equal to 0. So this is the wave function for 1, 0 state. This is the wave function for the 0, 0 state. And 1, +1 and -1 are simpler to write down. So let me now put in the normalizations over here. So this is 1/2. And this is 2. 2, this is 1/2. And the 1 minus 1 state would be oh, sorry. Sorry.
So no, that was so both are down. That's why you have beta in both, and if you write the +1, then you will have alpha in both these parts. Okay, so those are the wave functions. Now what we do is, let us try to evaluate taking these sort of the wave functions even when there is interaction between the electrons. So now what we are saying is, my Hamiltonian, so I'm erasing this part. See, up to this point, this is just a non-interacting electron system, okay? So this is the kinetic operator for the first electron. This is the potential operator for it. This is the kinetic energy for the second electron, and this is the potential operator for it. But now we are saying that they interact. They interact through the Coulomb interaction, R1 separation. And everything is written in atomic units. So given this, okay, and then what are these? So let me write this as well, these two constitute H1 and these two constitute H2. These are the one electron operators, and phi1 and phi2 are the eigenfunctions of the one electron operator. So H phi1 is some epsilon phi1 So this is what you normally learn when you do sort of many particle systems, that you have a one electron operator and you can construct its, solve for its eigenstates. If you have them, then using those eigenfunctions, you can construct symmetrized or anti-symmetrized wave functions. So what we have done here is, taken phi1 and phi2 be solutions of these one electron operators, Hamiltonians, and constructed the antisymmetrized state for 2 electrons. And then we are trying to see what is the effect of this term. If we now calculate the energy expectation value in that antisymmetrized state or states constructed this way, what do we get? So I'll do one case, which is for the singlet. So, and that will introduce the various terms that you come across when you try to evaluate these things. So what we are trying to evaluate is this. So I'll write a shorthand notation. So let me write this and then it will become clear. So this 4 is from the normalization constants. And then this state I'll write as so these are just the terms that you get from the 2 determinants that I wrote in the very first line. See, this is the problem I have because of limited board space that I cannot go back to it. But anyway, so if you take the 2 determinants with the minus sign for the singlet, and so you will get 4 terms. So these are those 4 terms. And the sort of convention here is that these 2 come with the indices R1 and S1. In any term, the first 2 will come with R1, S1, and the second one will come with R2. Okay. Just to simplify the notation, I have written it in this way. Okay, so this Hamiltonian is this Hamiltonian, which has 2 qualitatively different types of terms. One is this 1 electron terms, H1 and H2. And the other is the R12, 1 over R12 term. So I'll write the 1 over R12 term separately. So let us see first what we get with these H1 and H2 terms. So this has H1 plus H2, right? And there are 4 terms on each side. So you will have 4 times you will get the energy corresponding to the state phi1, and you will get the other term, the energy corresponding to phi2 4 times. So what we'll get is from that 4. Now let us write what we get from the 1 over R12 term. So when I look at terms like this with this with this, and when I'm taking the sort of matrix element, so I'm integrating over both R and the S variables, and integration over S variable will give me 1 when the spin parts are the same in the two wave functions, and when they are different, for example, this is fine, this is okay. When either the spatial or the spin parts are different, I'll get 0. Okay, so for example, when I take which one? If I take this with this, see the spin part here is alpha, this one. Here, sorry, I should be taking the wrong example. So when I take these two terms, this is alpha S1, this is beta S1. So such terms will give me 0. Similarly, when I take these, here I have phi 1 R1, here I have phi 2. So, or phi 2 phi 1 star, whatever. Star. So when I do the R1 integral, because of orthogonality of phi 1 and phi 2, I'll get a 0. So you have to keep track of what exactly you are doing. Wait a second. The R integrals is not going to be done this way because I have 1 over R12 in between, but the spin parts, whenever they are different, will give me 0. So with that, I'll get basically these terms. Okay, let's see. So when I take these two terms and do the spin integrals, I'll get 1s. So I'll get terms like and I'll get exactly similar type of term from here, except that the indices R1 and R2 will change. That doesn't matter. So I'll get 4 such terms, right? And then I'll get cross terms. So let us see which one I'm looking at. Yeah, so when I look at terms like this, what do I get? I have, so this, the spin integral here will give me 1. So this will give me a non-zero contribution. And when I look at the spatial parts, I get, this is phi 1 star R1. Then I have phi 2 star R2. And here I have phi 2 R1 and phi 1 R2. And I should get 4 such terms. Now, what I want you to notice is that I'm making, no, this is okay. So what I want you to notice is that these two terms are qualitatively different. So here I have phi1 star r1, phi1 r1 kind of terms. Okay, that's what gives me mod phi1 r1 square. Here I have phi1 r1 star, phi1 r2, phi2 r2 star, phi2 r1. So these terms are called Coulomb terms or Hartree terms or whatever. And these are called exchange terms. Okay, so with that, I'll write the energy as 1/4. Sorry, 1/4 is wrong. So this Coulomb term I'll write as C12, and that term I'll write as J12, that exchange. Now, if I take the this term, okay, and if you follow the same exercise, what we'll get is this. So the point here is that there is the two energies are different. If you did not have the electron-electron interaction, and in fact, if you did not have this term, so the only difference is coming because of this exchange term. Okay, and this exchange term is a consequence of one, the Coulomb interaction, and second, the exclusion principle, which forces you to write an antisymmetric wave function. If you did not have that, see, this is just a classical kind of term. So this is the charge density with the, if you multiply this by electron charge, this will just give you the charge density in a sort of volume d cubed r at the point r1 because of the electron in the orbital phi1. Similarly, this will give you the charge density in a small volume at r2. So this is sort of a classical interaction, and that's why it's called the Coulomb interaction. This is a consequence of the statistics. This is a consequence of antisymmetric nature of the wave function. So this is what I was emphasizing last time, that this difference. So now you have an energy difference between the singlet state and the triplet state, and that energy difference comes about because electrons interact and because they obey Pauli principle. Otherwise, you wouldn't have this difference. Now, once you realize that, the rest of it is sort of straightforward. No, there is one important piece of argument here, which is that in order to determine which one has a lower energy, you have to know what is the sign of J12. Okay. Now it turns out that J12, this without this sign, this integral, J12 is always greater than or equal to 0. So when it exists, it is greater than 0. And okay, so I'll give you a proof of that, but let's for the moment assume that J12 is greater than 0. So what do we do now? So what is the energy difference between the two spin states? In fact, if you work out this expectation value in the other triplet states, you will get the same energy. So it's twice J12, and we write that in the following way. So be conveniently expressed. So let me write this Hamiltonian, which was here. I mean, in this. So we call this singlet energy. We call this triplet energy. So why do we do that? So let us see what is the value of this object. So singlet is equal to 0, triplet is equal to 1, and I have s times s plus 1 equal to 0, s times s plus 1 equal to 2. And with that, you can show that s squared minus 1 is going to be twice this 1 is 2 plus half. All right. For S1 equal to S2 equal to half for spin half objects. So, so with that, so basically, what you will have is for spin half objects. So once you realize this, you can calculate its value. So this quantity, let me write it here, twice S1 is 2 plus half will be minus 1 for singlet. This just comes from the values of s that you have, and twice s1 dot s2 plus half is plus 1 for 30. Okay, now once you have evaluated these, you just place those two values in for this factor over here, and you will easily see that when you take the value for singlet, H will give you the singlet energy, and when you take this value for the triplet, H will give you the triplet energy. So this is a trick of writing H in terms of S1 dot S2, so that in these two situations, you recover the energies of the singlet and the triplet states. So what do we gain in the process? In the process, if we are not sort of interested in the, for example, this constant, then this whole thing, and we know what is the difference, epsilon, the singlet triplet energy difference, which is twice J1. So in terms of that, then this Hamiltonian is written as some constant minus so this is how you derive an effective spin-spin interaction. Let me repeat, there is no fundamental interaction between spins. So the original Hamiltonian is just this. This is a very, very basic fundamental point. The original Hamiltonian is this. All the interaction you have is this. I mean, these are not so crucial because these are just one particle potentials that each electron experiences. But the crucial part is this, the electron-electron interaction. So this plus the fact that you write antisymmetric wave functions give you this term, which is the exchange term, which causes the energies of the singlet and the triplet state to differ, this one and this one. And once you have that, then you can sort of express this original Hamiltonian in a form so that you recover the singlet and triplet energies for appropriate values of this term, and therefore you can write the Hamiltonian like this. So you generate an effective spin-spin interaction. In what situation? In a situation where the orbital part is fixed. The orbital parts are fixed by phi1 and phi2. And we have noticed, we have also assumed here in this whole analysis that one electron is residing in phi1, the other is in phi2. So given this constraint, we are now trying to figure out what is the spin configuration that lowers the energy. And it turns out that the triplet state has a lower energy. And that is what we are expressing in terms of this effective spin-spin Hamiltonian. So there was a bit of a misunderstanding as we were discussing in the last class. So this should be clear now that there is no fundamental spin-spin interaction to start with. It's an effective way of writing the consequence of Coulomb interaction and Pauli principle. And okay, so what did we find? We find, without proof, I just stated that J12 when it is non-zero is greater than 0. So minus J12 is negative, which tells you that the spins would like to align with each other, S1 and S2. So that at least explains a ferromagnetic coupling between two spins, which was sort of proposed as the explanation for Hund's coupling in atoms. Questions at this point?
Sir? Hello,
Yes.
sir. Sir, in this Hamiltonian, we have not find the exact eigenvalues. Instead of that, what we are doing is kind of like perturbation treatment. So the eigenvalues that we get, how much faithful are these?
Firstly, this is, well, I won't even say this is a perturbation. I mean, well, I'm just claiming that the Slater determinants I have constructed are the wave functions even when I have interaction. So which is of course not true, as you know. And the eigenfunctions are of course not going to remain the same if you solve the problem by including electron-electron interactions right from the beginning. So neither are epsilon 1 and epsilon 2 going to remain the same, nor are the functions phi 1 and phi 2. So if you really solve the interacting problem, and this is a good question actually, because if you have followed this argument, this was proposed by, I think, Slater some 80 or 90 years ago as an explanation for why spins like to sort of point in the same direction or tend to align. So as you see, the whole argument is based on the assumption that phi 1 and phi 2 remain the same, irrespective of how the spins are oriented. Now, very recent calculations solving the interacting problem have shown that that assumption is incorrect. So the wave functions themselves, phi 1 and phi 2, change depending on whether you are in the singlet state or the triplet state. Now, once that happens, if the functions phi 1 and phi 2 themselves change, then not just the interaction energy, what changes is also the electron nuclear interaction energy. This calculation is for a single atom. So therefore, if the phi's change, then the epsilons change, and there are different components to epsilon, the electron kinetic energy and the electron nuclear interaction energy. And all those quantities actually change. And because those change, ultimate analysis pointed out that here the argument is that in the triplet state, the electron-electron interaction energy is lowered because J12 after all comes from the Coulomb term, and therefore it has a lower energy. There it turned out that the electron-electron interaction energy is actually not lowered in the high-speed state. It's rather the electron kinetic energy which is lowered in the high-speed state. So the final argument is far more subtle, but at this level, for this course at least, as long as you understand the assumptions are that the wave functions do not change, the eigenvalues do not change between the singlet and the triplet states. With those assumptions, what we find is that in the triplet state, the electron-electron interaction energy is lower, and that gives us a justification as to why electrons would like to align their spins with each other, which gives an explanation for at least the ferromagnetic coupling. All right, are there any other questions? Okay, the two things that I have to do next. Let me see. Sorry. So I call this, let's say, call this some function f of Okay, so this becomes phi star of R1. So with that, and well, this is 1 over R12. This is some interaction V, which I can write as a function of, generally it's a function of R1 minus R2. So this then becomes so let me write the two integrals separately. So this is, like the convolution of these two functions, v and f, with some fixed R1 here. And so that can be written as, so the exact form would be you can take properties of Fourier transforms. This is what. Now I have an R e to the I k dot R1 here, which I can pull with the R1 integral. So I have this, and then I have the k. Now this is just f star. Sorry, this was R. Sorry. So this is just f star k. So this k integral, of course, involves this. So, so then I have. So it doesn't matter what functions f are. Now this is, I know the Coulomb interaction, and I know its Fourier transform. So this is not in atomic units. Hope I wrote it correctly. Just no, which obviously tells you that this is greater than equal to 0. So this is the argument that the exchange is greater than or equal to 0. All right. So that completes that argument why the triplet would have lower energy. this is another important point in magnetism. There are no classical magnets. There are several, I mean, at least 2 points one can make about that in support of this. Firstly, whatever we discussed so far, we saw that it's a consequence of interactions and Pauli principle, which is a consequence of the fact that electrons are spin-half particles, they are 4 fermions. Now this spin-half, this is of course a purely quantum phenomenon. But then electrons are charged particles. So when they have orbital motion, you can have magnetic moment because of that orbital motion. You probably are familiar with that. So this orbital moment. So now if we consider orbital moments and see what effect that can have or what effect external fields can have on that, whether external fields can sort of give moments in such systems. So let us consider a purely classical situation where electrons are moving in some external magnetic field. Okay? So the Hamiltonian, I can write for a number of electrons. So I will write the Hamiltonian as well, probably have electrons. In order to calculate this magnetization, what I'll do is I'll calculate the classically, I'll calculate the free energy and take its derivative with respect to the magnetic field. So that will give me magnetization. Okay, for that, what do I do? In order to calculate the free energy, I calculate the classical partition function, which is, I'll just quickly write down the expression. So remember, this is a classical Hamiltonian. Now there are 2 parts. This part, so when I'm doing the P integral, I look at this part of the Hamiltonian. And since all the sort of components of all P's are integrated from minus infinity to infinity, I can do a shift. So I can shift Pi to be the mu Pi. But then again, the limits would still remain minus infinity to infinity. So therefore, what happens is that A completely drops out of this. So because A completely, A is the vector potential, of course. So because A drops out of this, the classical partition function has no A dependence or magnetic field dependence. And if it has no magnetic field dependence, so then this F free energy will also have no magnetic field dependence. So therefore, in will be zero. So this theorem, which is goes by the name tells you that even for orbital motion, an external magnetic field cannot bring about a magnetization in an electron system if you treat them classically. So any such magnetic order is necessarily a quantum effect. And of course, spin is a quantum phenomenon. So any magnetic moment coming because of electron spin is of course of quantum origin. So magnetism is a purely quantum phenomenon. There is no classical magnetism. Sometimes we do use the word classical, but you have to really understand the context in which they are called classical. Okay, so we have made some progress. We have understood how we generate some effective spin-spin interaction. We have also understood that there are really no classical magnets. We have, I mean, magnetism is essentially a quantum phenomenon. But then remember, when we discussed that energy difference between the singlet and the triplet states, the assumption was that the two states we took, phi 1 and phi 2, they are orthogonal to each other. Now that is true when I'm talking of, let's say, a single atom. I have, let's say, two d orbitals, and I'm asking why should the electrons in these two d orbitals align with each other rather than being up and down. And we got the answer that by aligning their spins, they lower the exchange energy. Fine. But what happens when you look at a solid? Because then what happens is different atoms sitting at lattice positions have moments on them, and these moments align. So the electrons sitting on different atoms are responsible for the moments, and those atomic orbitals, assuming that the moment is still coming from atomic orbitals, so those atomic orbitals on different atoms, they are not orthogonal to each other. Okay, so that's a question one can pose. Also, the earlier analysis between singlet and triplet showed that the exchange always favors a triplet state. So that explains ferromagnetic coupling, where the spins tend to align with each other, their spins. But if you look at the materials that are known to us, there are far many more antiferromagnetic materials in which alternate spins are pointing up and down rather than ferromagnets. So that analysis cannot explain how an antiferromagnetic exchange coupling is generated between different moments sitting on different atoms. So then that is the question we have to now understand. How can we generate effective antiferromagnetic coupling between spins? So we'll study two different mechanisms which give rise to antiferromagnetic coupling. So the mechanism we studied in the case of two orthogonal orbitals, that is of course an example of what we call direct exchange. And now we will talk about direct exchange between orbitals that are not orthogonal to each other. And subsequently, we'll talk about something called kinetic exchange. So that will come later. By the way, before I forget, if you can see, this is the textbook I'm following. I don't know if a PDF of this is available, but you can check. Have you, I mean, are you doing your quantum 3 course in this semester?
Yes.
Yes, sir.
And have you been taught any molecular physics, for in particular Hartley-Fock theory or Heitler-London theory of H2 molecule? Have you been taught these things?
No.
No. Okay. All right. So what I've discussed here is essentially the Heitler-London theory of H2 molecule. But that will give us, what we are aiming at. So what we have are two hydrogen atoms, and what we consider are the two 1s orbitals on these two atoms. And let me fix the notation first. I'll call the positions of these nuclei as RA and RB. And there are two electrons, so their coordinates will be denoted by R1 and R2. And then the full Hamiltonian of this system governing motion of the two electrons is the terms should be obvious. And when I take something like this, that is what we should.
Sir, no RA-RB term?
Sorry, say that again.
No RA-RB term?
Okay, I mean, that's considered a classical term. I mean, that does not really affect solution of this Hamiltonian or eigenvalue problem of this Hamiltonian. Okay, you can always add that to your total energy at the end. So we are
Okay, sir.
So we are bothered about the quantum problem of the electrons. Of course, in the total energy, that term is there, sure. So things like this will be called the atomic Hamiltonian. So the atomic Hamiltonian is R minus some particular R, it could be RA or RB, is the energy of the boundary state. Oh, sorry. Yes. So what we'll do is we'll use the shorthand notation that phi 1 is of the atom at A will be termed phi A. And And of course, phi A and phi B are not orthogonal to each other. Now they are the functions of two different atoms, so they are not orthogonal. So we'll have some overlap in here. So these are things we have come across in different contexts. We call that. There is a potential conflict here. So let me call this capital. No, I don't call this capital S. We used S for spin, so let me call this L. So what is the aim here? The aim is to sort of diagonalize this Hamiltonian in the subspace where this is called subspace of neutral configurations, where there is one electron on each atom. Okay, so one electron is in orbital phi A, the other electron is in orbital phi B, and because these orbitals are the electrons are indistinguishable, I don't know which one is where, so that will give me more than one turns. And because my Hamiltonian is completely spin independent, so therefore the wave function that I construct should be, therefore A square and AZ should be good quantum numbers. So I try to construct wave functions that are eigenfunctions of A squared and AZ. Okay, so basically we try to write down wave functions for neutral configurations that are eigenfunctions of A squared and AZ. Again, we have similar type of exercise. So let me write these 4 wave functions. Now they will be slightly different. You can immediately identify this as one of the triplet states where both electrons are common. Obviously, I'll have a similar state with both electrons down. So this is basically the 1 plus 1 state. Similarly, I will have I'll write the 1 minus 1 later. Let me first write the 1 0 state, which I call psi 2. And the other difference is this normalization, because now we have a finite overlap integral, which is not 0. Had it been 0, you would have just got a 1 over root 2. Now, as before, the 1 0 term will involve basically 4 terms rather than 2, but they look the same as we wrote earlier. And I'll have A1 minus 1 term, which will be similar to that. And then I will have a 0, 0 term. Similar. So these are the four states we have in this part of the Hilbert space, where we don't consider configurations in which both the electrons are sitting on the same orbital. We'll come to that later. These are called ionic configurations, and in fact, they turn out to be important when you have electron-electron interactions. But we'll come to that later. Okay. Now, what is the time? We have some algebra involved. In fact, quite a bit of algebra involved. So I am not sure I can finish it very quickly. So maybe this is a good point to stop for today, and next time we'll start from here. So I'll rather wait for any questions that you have.